Okay, the section 8.3 on Newton-Euler inverse dynamics. Finally, we will derive the iterative Newton-Euler method to obtain the inertia and the centripetal and the Coriolis matrix and gravity. Okay, let's consider the inverse dynamics problem for n-link open chain connected by 1 degree of joint, 1 degree of freedom joint, such as the revolute or prismatic. Okay, for given joint position theta and velocity theta dot and acceleration, those are given. The objective is to calculate the right hand side of the dynamic equation. Okay, so theta and theta 2 dot, theta dot will be applied to obtain the right hand side, ultimately to obtain the torque. Okay, so inverse dynamics will be used to make your own controller. Okay, the recursive inverse dynamics algorithm composed of the two steps. The first one is about the forward step and backward step. In the forward iteration, the position, velocity, and the acceleration of each link, such as the twist and the time derivative of twist, will be obtained from the base to the tip. On the other hand, the backward iterations, force and moment, include such as the wrench experienced by each link will be propagated from the tip to the base. So forward and backward will provide inertia and nonlinear terms of dynamics. And here's H. Okay, let's derive. By the fixed reference frame I will be attached to all the time to the center of mass of each link. There is a given condition. The base frame is denoted by the 0, and the end effector frame is denoted by the n plus 1. Okay, it is fixed to the frame n. Okay, here's at the home position, all joint variable will be set as 0. At that time, the constant m can be obtained from the home position. Mij belonging to SE3, such as the R4 times 4. So, the typical example of the M will be the homogeneous transform. It implies configuration of J frame in terms of the I frame. So coordinate is used in the I frame. Is it right? On the other hand, Mi is equal to M0I. So configuration of the I frame in terms of space frame. Okay. So we should memorize this constant matrix concept. Okay. So Mi minus 1I can be obtained by using the Mi inverse times Mi. This matrix will change the coordinate I minus 1 into the space frame 0, and then it will go through from 0 to I. On the other hand, I minus 1, actually it implies the computation of I minus 1 frame in terms of the I. It can be obtained the inverse one. Okay. It is all the time constant matrix because every joint variable will be set as zeros. The screw axis of the joint I expressed in the link frame I is denoted by the A. So A is the constant. Square axis of the A is constant. The same square axis can be expressed in terms of space frame denoted by the 0. It will be denoted by the SI. So SI and AI express the same one, same square axis, but the coordinate is different. So adjoint mapping will be required between the A and the S. Okay? Tij belonging to SE3 homogeneous transform will be the computation of the frame J in terms of the I frame. And Ti-1I, the computation of the I in terms of I-1 frame. And then Ti-1 theta can be obtained by the inverse of matrix of the Ti-1I theta I inverse. So Ti-1I will be obtained. The previous home position I-1 I, and then actually it expressed the frame I with the 0 join position, and then E2 AI set I will be multiplied to obtain the effect of the set I. Okay? The inverse matrix, by taking an inverse of both matrices, so E2 minus AI theta and the inverse matrix of the M should be multiplied. It is the very systematic way. Okay. From now on, every twist, every length will be denoted in terms of I frame by itself. Okay? So we are using the body frame all the time in this derivation. And the GI, maybe you know the GI. GI is the special inertial matrix of the link I expressed relative to the link frame I. So every notation will be expressed in terms of link I frame. Okay? Maybe you know the 3x3 inertial matrix and constant M mass link mass. Okay? So GI will belong to R2 6 times 6. Okay, with these definitions, we can recursively calculate the twist and acceleration of each link, moving from the base to the tip. Okay, twist Vi of link I will be the sum of the twist link I-1, but it should be expressed in terms of the I. Okay, so adjoint map it will be required to change the coordinate. And the another twist should be added because due to the joint velocity set I dot. Okay, so this is the square axis of the link I. Theta dot will be influence the twist of the Vi, and the previous twist should be expressed in terms of I coordinate. So adjoint map will be required. So two terms, the add of the two terms will be used to denote the twist Vi. Okay, let's take the time derivative to obtain the acceleration. Can be found recursively taking the time. Let's take the time derivative. Okay, Vi dot like this. Okay, the A is the constant, so set I 2 dot is required, and the product of matrix and vector, so we will take the time derivative of product, so V dot and adjoint dot will be required. Okay, let's consider the time derivative of adjoint T I minus 1 and the V I minus 1. Okay, here maybe you know, if we have the homogeneous transform Ti I minus 1, maybe the 3 by 3 rotation and the 3 by 1 vector can be used to denote this homogeneous transform, and the square axis is constant belonging to R to 6. Okay, so this adjoint map can be obtained R and the P cross R. Okay, let's take the time derivative of both this matrix 6 by 6. Okay, the first one. Okay, R I minus 1. Maybe we know that the R inverse, the R inverse R dot will be omega B matrix, square symmetric matrix form of the omega B. So R dot will be R omega B. Okay, by exchanging both parts, omega B R, the minus sign is required. So minus omega B is corresponding to omega theta I dot. Okay, and then R according to this definition, and 0 is the 0, and then it has two terms. The P dot is equal to V theta I dot, but the P indicates from the I to the I minus 1, so this is the minus direction, so minus is required. And then the R dot has show the same matrix from the 1 by 1 block diagonal matrix, and then R dot is here. Okay, this matrix can be decomposed to two big matrices, such as this one and adjoint Ti I minus 1. Okay, so adjoint Ti I minus 1 and Vi will be equal to Vi in viewpoint of the I frame. Okay, so this is the Vi, and minus can be extracted to the outside. So it is equal to minus leaf bracket of AI theta I dot. Okay, like this, and then twist I. The both part, actually the leaf bracket of the A theta I dot Vi can be exchangeable. At that time, the minus can be exchanged as a plus. Then adjoint Vi AI theta I dot. Okay, so this term is used to denote to express the acceleration. Okay, so this part is added here. Okay, so the first term is related to the joint acceleration of theta I 2 dot. This is influence effect from the previous link acceleration. It is related to the velocity product between the twist and rotational velocity of the rotational acceleration of link I. Okay, this is the product. Okay. After determining all the link twist and acceleration, moving from the base to the last link, and then we can make the length equation acting on the link I from the end side to the base. Okay, let's consider the figure 8.6. This is the center mass of the link I. Here's the twist and the acceleration is applied. And the previous link will make the reaction force. Reaction force is denoted by the length Fi plus 1, but the link I will have the reaction force, reaction length, so minus adjoint Ti plus 1 I transpose is required to express the subsequent length should be expressed in terms of the previous link, okay, using this notation. And then Fi. Fi is unknown. Here, joint axis is the Si, so it is denoted by the Ai. Okay, so in the previous dynamics, maybe in the previous lecture we have derived this equation. Is it right? Here, the force part, the length part, can be decomposed two terms. This one and this one. So we have this equation. In the forward stage, we have determined the Vi and the acceleration. In the backward stage, for given Fi, we will determine the Fi plus 1 is given and Fi is unknown. So in the backward iterations, we will determine the every length from the last to the beginning. Okay, so as you can see here, only unknown Fi is here. And then the Fi and Ai, the inner product of this part, will generate the rotational torque. So torque can be obtained by projecting the Fi length into the square axis. So this value can be obtained from the inner product. Okay. Okay, let's summarize the Newton-Euler inverse dynamic formulation. Okay, as mentioned before, the frame 0 to the base and the frame 1, 2, n will be assigned to the center mass of the link I, 2, n. And the last frame, n plus 1 at the end effector, it is fixed to the frame n. Okay? And then mi, I minus 1, it is the computation of the I minus 1 in terms of the I when the every theta as zeros like this. Okay, so M is the constant matrix. AI is also constant matrix denoting the square axis of the joint I expressed in terms of I frame. Maybe you know the GI is 6 by 6 special inertial matrix of the link I. And then V0, the twist of the base frame in terms of the 0 coordinate. Okay, 0 frame. Maybe it will be 0 all the time. And then the gravity vector expressed in the base frame. Okay, so acceleration of the V0 will be the angular acceleration and the linear acceleration. the initial acceleration will be given as a 0, but initial linear acceleration is replaced with the gravity vector. The gravity is treated as an acceleration of base in the opposite direction. In many cases, we choose the gravity vector as a downward, so negative normally is used. And then the end effector length, Vt, Ft, moment and the force is given by the environment. So it will be used to obtain the Fy backward iteration stage. Okay, for given theta I dot, and the theta I 2 dot, here's from the I as a 1 will be applied to here, then we can obtain the T1 0 and then V1 and then V1 dot. And then the I will be increased to the 2, then T2 1 and V2 dot. Like this, we can determine the n minus 1, Vn, and Vn dot. Okay, completing this twist and acceleration, then we will apply the backward iteration to determine the Fy. Okay, for given last end effector length, it can be expressed in terms of I frame using the adjoint map, and then inertial force will be applied, okay, using the V and the V dot. Okay, after obtaining the Fy, we can extract the joint torque. The Fy should be projected to the joint square axis. The remaining terms, except the tau I, will be the constraint. Okay. Okay. This is called as recursive inverse dynamics matrix. Okay. Let me show you how to use this iterative method to obtain the nonlinear term and inertial matrix. Okay. Those will be used in driving the pole dynamics later. Anyway, okay. We know that this algorithm is equivalent to the tau inertia theta 2 dot plus nonlinear term theta and the theta dot. Okay, in order to obtain the h using this algorithm, okay, from here we can know that the theta 2 dot should be 0. Then tau will express h, is it right? So in this algorithms, we will apply all the theta I 2 dot set to zeros. Okay, so this theta and the theta I dot is the current status, but theta I 2 dot will be given as 0. So we can determine the T and V and V dot, but this term will be 0 all the time. Okay? Every iteration, it should be the 0. The remaining terms are remain as a current 1. Then, through these stages, we can determine the V1 through Vn, V1 dot through Vn dot. These kinematic parameters will be applied to the backward method from here and here. Okay, here we will apply the backward Fy, F1, Fn, Fn-1 through F1 will be obtained. By multiplying the AI, we can determine the F tau n, tau n-1, and the tau 1. Okay, let's come back to the original status. in this algorithms, actually this algorithm implements this one. Theta 2 dot is given as a 0, so this term is 0. So this tau, by collecting as a vector, tau 1 through tau n, it is corresponding to the h. Like this, just one iteration forward and subsequent backward iteration, the result will be the tau. It is corresponding to h vector. Okay? So it's very efficient way to obtain the h. Okay, let's obtain the inertia. Okay, one more. It's very interesting to obtain the h matrix, h vector from this algorithm. Okay. Okay, one more. Tau is the m theta 2 dot plus h dot. As mentioned before, this iteration algorithm will implement this inverse dynamics. Okay, so in order to obtain the inertia matrix, not vector, we will apply 0 theta and 0 theta dot. Okay, and okay, this is the matrix. This is the vector. So M11, M12, blah blah, M21, M22, blah blah, blah blah, Mn1, like this. Okay, in order to obtain the first column vector of the inertia matrix, let's assign 1, 0, 0, blah blah 0. At that time, we will get the N11, M21, blah blah, Mn1. Is it right? So we will set this is the 0. Okay, this is the given constant. I'm sorry, that this is not 0. This is the given. Theta dot is 0. Theta 2 dot. In order to obtain the first column vectors, theta 1, 2 dot will be the 1. Theta 2 dot is 0. Blah blah. Theta n 2 dot will be the 0. Okay, this variable will be applied to here. Then we can determine the v1 through vn, v1 dot through vn dot. This kinematic data will be applied to here. So by iterating this method, we can get the tau 1, tau n through tau 1. It is corresponding to mn1. This is the m11. So by collecting this vector tau, it is corresponding to the first column vector of the inertia matrix. Okay, if you wanted to obtain the second column vector, maybe the first one will be the 0, the second acceleration will be 1, other part will be the 0. Okay, so this is the 0, this is the 1. Will be applied to here. We have the new v1 through vn, v1 dot through vn dot. This data is applied to here, and then we can get the tau n through tau 1. It is corresponding to mn2, blah blah, m12 is obtained as a result of the tau. Like this, we can determine the second column vector of the inertia matrix. If you apply this kind of things n times, we can make the inertia matrix. Okay, it is the recursive Newton-Euler method to obtain the m and h. Okay, it is very important. It's very efficient way to obtain the inertia. Okay. Okay, till now we have talked about the iteration method to obtain the m and the h. On the other hand, we can write down, we can obtain the closed form m and the c and the g. So I will explain it. M, C, G can be obtained by using the very big matrix. Okay. If we wanted to obtain the inertial matrix only, at that time we can use the kinetic energy. Maybe we know that the kinetic energy in terms of the theta dot and the theta, it will be equal to the sum of the twist and the special inertia and the twist. Okay, both are same because the inner energy is not dependent. It's not dependent on the coordinate frame, so it should be equal to each other. Okay, here we know that the twist can be obtained by using the Jacobian. Okay, this will be applied to the here, and then we can get this Jacobian transpose G and the Jacobian. Okay, sum of this part will be equal to inertia. Okay, so just obtaining the Jacobian and the special inertia, you can determine the inertial matrix. Okay. On the other hand, we will collect the every equation of kinematics and every the backward equations will be collected to make the MCG here. Okay. Okay. Later I will explain it. Okay. From here. Okay. Okay. Let me write down the twist equation. Maybe you know the first twist V1 is equal to A1 theta 1 dot plus other joint T1 0 the V0. Is it right? And V2 A2 theta 2 2 dot and other joint T21 V1. Is it right? Let me check the correctness of the equation. Okay. Maybe the third twist will be obtained A3 theta 3 dot and the other joint T31 and V2. Okay, let's collect this matrix. Okay, this vectors V1 through V3 is obtained A1, A2, A3. Other terms will be the zero matrix and theta 1 dot, theta 2 dot, theta 3 dot plus this other joint should be multiplied. Okay, this is the initial condition, so let's extract. The remaining terms will be the 0, 0, 0 and the other joint T21, 0, 0, 0, other joint T32, 0, and then V1, V2, V3. Okay, the first one, this term will be extracted to the outside. The second terms have the V1, is it right? The same one. The third term will be the other joint T32 times V2. So it completes this equation. Okay, like this. In order to generalize this kind of method, we will introduce the stacked vector and the matrix. Okay, let's stack. V1 through Vn belonging to R6n, if you have the 4 joint at that time, R24, if belonging to R24, 24 elements will be aligned into the downward. Okay, the length is also can be stacked like this, F1 through Fn. And then the square axis of the joint A1 through AN can be stacked. It is vector, so the total matrix will belong to R to 6n times n. Okay? The G1 through Gn can be stacked in the diagonal matrix. Then it will be denoted by the G. It belongs to R to 6n times 6n, very big matrix. In the case of the 6th degree of freedom, this G matrix belonging to 36 times 36. And the Lie bracket, the small joint V, can be stacked in the diagonal matrix. Okay? And then the joint A zeta dot is stacked. Okay, one more. The W. In order to implement this part, the previous link will describe it in terms of the subsequent frame. Okay, so this matrix will be required. The diagonal is a 0 matrix, but the off diagonal, downward off diagonal will have the adjoint map, okay, to implement this equation. Okay, and the initial condition, this part is separated, so it is stacked in the V base. The first 6 element is non-zero, but remaining terms is 0. And with that base, it has the gravity vector in here. The remaining terms are 0. Ft, the length of the end effector will be starting point, so the last part will be stacked. Okay? By defining this kind of big matrix, we can obtain, okay, V is equal to W and V A zeta dot V base. Okay, one more. Okay, V1 dot is adjoint T10 V1 plus A1 zeta 1 dot. Okay, it will be collected to the V base. It is stacked here, but first part will be the 0 over this part. Is it right? Because W has the diagonal terms as 0 matrix. Okay, like this we can write down the V as a WV plus A zeta dot and the V base. Maybe the V dot will be obtained the similar form. W is required to denote the adjoint map from the previous link. Okay, the remaining terms are the same. And in the backward iteration can be stacked in the F vector, the stacked vector, using the W transpose, because the adjoint map transpose is required. Okay? And then those are same. It provides the initial condition such as the tip length and the inner product of the A and F will provide the tau vector. In here, every element is very big stacked vector, very big matrix, but it will provide the closed form of the M and the C and the G later. On the other hand, we have 2V in here. We know that, let's take the 3x3 W, okay, the 0, 0, 0, adjoint map T to 1, 0, 0, and 0, adjoint map T 3 to 0. Okay? Let's multiply it. Square, double square, the same one. 0, 0, 0, adjoint map T 2, 1, 0, 0, 0, adjoint map T 3 to 0. Okay? The first law will be the 0. The second law is the 0. This is also 0. This is the 0. On the other hand, this will be the adjoint map T3 to T21 and 0, 0. So it can be combined to denote the 0, 0, 0, 0, 0, 0 adjoint map T3, 1, 0, 0. If you apply the one more, maybe you have the 3 times 0 matrix. Okay, like this kind of nilpoint matrix, it is called as nilpoint. By multiplying the n times of the W, we'll have 0 matrix. So maybe you know that the 1 over 1 minus x will be expanded using the 1 plus x squared, blah, blah, blah. Do you remember this kind of Taylor's expansion? It is extended to the matrix. 1 minus W inverse will be the identity plus W squared, blah, blah, to the infinity. But W n times of W will be the 0. So the last term will be the W n minus 1. Okay? So by adding from the identity to the Wn minus 1, we'll have identity plus W. W will have, other terms are 0, only these terms are given. W squared, maybe this part. Wn minus 1 times provide this equation, this term only. So by adding the every terms, we'll have this matrix. It's very easy to understand and memorize in your mind. Okay, so it's very useful equation. Let's denote this is the L theta, because it depends on the computation. Okay, so from here, WV plus A theta dot plus V base. Okay, let's move to here. I minus WV A theta dot plus V base. Let's take the inverse of this one. The inverse will be the L and A theta dot V base. Like this, we can make the I minus W inverse. Then we will introduce the L matrix. By using the L, the earlier matrix equation can be written using the L transpose. Okay, here, let's apply this F to here. Maybe the A transpose, L transpose, and the G, V dot is this one. The V dot will be given here, and leave bracket V transpose, and G, V will be applied to here, V, okay, plus F tip. Okay, by expanding this equation using the V dot and the V, then the result will be the tau. So this matrix equation will be equal to M theta 2 dot and the C and the G and the J transpose F. So by comparing both terms, we can know that the M is equal to A transpose L transpose G and LA. So by multiplying the 5 big matrix, we can determine the M. So like this we can derive the closed form of the inertial matrix. A transpose L, G, L, A. Okay? How about the C? By comparing both equations, we can determine that this big matrix will be corresponding to the C. On the other hand, this is the G. Okay, like this we can derive the closed form of inertial matrix, Coriolis centripetal, and the gravity. Okay, we have derived two methods. The first one is iterative Newton-Euler, and the second one is the closed form of the MCG. Okay. Next topic is about pole dynamics. In the previous section 8.3 and 8.4 is about inverse dynamics. Inverse dynamics is used to make your own controller, because if you want to use the dynamic control, MCG is required. So we should derive the MCG formula. On the other hand, the pole dynamics is used to simulation. Okay, so pole dynamics is not used for your control. It's just for your simulation, dynamic simulation. Okay, pole dynamics problem is about the for given tau and theta dot and tip length, we will determine the theta 2 dot at the next time. So tau is given by the controller and the current stators, and the environment provide the F tip. From this information, we can determine the theta 2 dot from here, this one. And then we will apply the integration method to obtain the theta dot and the theta. Okay, so these terms, actually I have already explained them. Okay, H is obtained by calling the inverse dynamics algorithm by setting the theta 2 dot as a 0 vector and the external pulse as a 0. Then by calling the inverse dynamics iterative method, we can obtain the tau that is equal to the H vector. Okay. On the other hand, inertial matrix case, we should do inverse dynamics algorithm n times, because in here's 0 gravity and theta dot, 0 theta dot, and 0 is anti-vector poles. In the first call, the column vector of the theta 2 dot, all the 0 except first row. So 1, 0, 0, 0 should be applied to obtain the first column of inertial matrix. In the second call, theta 2 dot should be the 0, 1, 0, 0, 0. Then the result will be the tau. Tau will be equal to the second column of inertial matrix. Actually, I have explained it before. So the tau vector returned by the ith call will be corresponding to the ith column of the inertial matrix. After n calls, the n by n matrix is constructed. Okay? It is very efficient way to obtain the inertial matrix. On the other hand, if we wanted to use the closed form of the inertial matrix, at that time inertia is obtained. A transpose and L transpose G and then LA. By multiplying this kind of big matrix, you can determine the inertial matrix. This is alternative way to obtain the inertial matrix from the algorithm, but this is more efficient. So Newton-Euler method is recommended to use by you. Okay, the pole dynamics case in here, maybe it has the M and H and the J transpose F. Both terms are included to here. Okay. So the result will be the theta 2 dot. Okay, in order to second order dynamics into the two first order, we will extend the state vector to the 2n dimensional. So the n dimensional theta will be assigned to q1, n dimensional theta dot will be assigned to the n dimensional q2. So 2n dimensional state vector is required to obtain the like this kind of matrix, this kind of form. Okay. So as you know, the q1 dot is the vector. Maybe the q1 t plus delta t minus q1 t denoted by over delta t. Maybe the q1 dot is approximated like this. Okay, so let's apply this approximation. Then q1 t plus delta t will be obtained q1 t plus q2 delta t. So we have this one. Okay. On the other hand, q2 dot, the similar form is applied, then we can determine this equation. So by obtaining the fd for dynamics and the delta t, the scalar variable will be applied, and the q2 is added, current velocity is added, then the result will be the next time velocity. This is the next time computation. Okay. Okay, Newton-Euler integration algorithm to obtain the pole dynamics. Okay, everything's maybe you can understand the initial condition and the delta t. Okay, the final time is the 1 second, and is chosen as a 1000, and delta t will be the 0.001 1 millisecond. Like this, we can determine the delta t, and for given initial condition from k to the n minus 1, from here 0 to 999. Let's iterate this equation. First term is about the theta 2 dot, and then the delta t is applied, so we can determine the next time theta and next time theta dot. So animation or simulation, this kind of method can be used to show the dynamic effect. Okay, the result will be assigned to the continuous theta and the theta dot. Okay. Okay, this is the first order integration. If you wanted to make this algorithm more exact, then second order or fourth order Runge-Kutta can be used. Okay? Actually, the MATLAB making use of the variable step fourth order Runge-Kutta instead of the Newton-Euler integration, because Euler integration is very simple, but the numerical error can be stacked, can be collected to show the dynamic motion. Okay, I'd like to recommend you to use the fourth order Runge-Kutta. Maybe if you have used the MATLAB in there, OD23 and OD34, it is corresponding to the Runge-Kutta. Runge-Kutta is a more stable algorithm to obtain the dynamic motion. Okay, the task space dynamics. For given joint space dynamics here, we know that the twist is related to the Jacobian. Okay, so let's take the time derivative of the twist, then j dot theta dot j theta 2 dot, because it is product term. The product differentiation should be implemented to here. Then if j has the inverse, at that time j inverse twist will provide theta dot. How about the theta 2 dot? V dot minus J dot theta dot, and then the J inverse should be multiplied in front side. Okay, this theta and the theta dot is applied to here, and here. Then we have the very long matrix. This is a theta 2 dot. This is a theta dot. By rearranging this equation according to the V, and then we will multiply the both sides, J inverse transpose. Okay, J inverse transpose, J inverse transpose, J inverse transpose, J inverse transpose. Okay, every term will have the J inverse transpose because J inverse transpose will provide length. Maybe you know that the tau is a J transpose length. So the inverse of the J transpose is required to obtain the length. So this is corresponding to the length. And how about this 3 matrix will corresponding to lambda, task space inertia. And the remaining 2 terms will be corresponding to the nonlinear terms. So J inverse transpose and J inverse will be equal to task space inertia. Okay? And effector inertia. In order to obtain this task space dynamics, J should have inverse matrix. J must be the invertible. At that time, one-to-one mapping can be obtained. So we can easily derive the task space inertia in the nonlinear terms. Actually, the remaining section is about 8.789. I will skip them because time is running out. Actually, the section 8.9 is very important. It is containing the actuator dynamics into the Newton-Euler method. Every robot system has the actuator. So actuator dynamics should be considered in deriving the dynamic equation, inertia matrix, and this C and G. So I'd like to recommend you to read the section 8.9 for your practical use of the robot system. Anyway, I will skip the remaining 3 sections. And you have homework. Okay, the due date of the homework will be the final exam date, maybe June 18. I'm not sure. I wanna postpone the final exam to the June 25, but the university step is not allowed the extension of the midterm exam. The university requires to finish the lecture before the June 19. Okay, so I changed my mind. So you should take the final exam on June 18. Maybe the Thursday. I will post this kind of information to the website of class. Okay, the homework will be the 8.1, 8.2, 8.4, 6, 7, just 5. But it's not easy. Anyway, you should try to solve this exercise. If you have some question, let me know that. Okay? Okay, thank you.